Welcome back to another video. Well, today we'll start digging into quantum mechanics by solving the Schrödinger equation, or at least not solving but simplifying them, and to not very narrow spectral solutions, because we're going to assume that the potential is time independent. And before doing that, let's review what we've seen so far, even though I still have to upload the video on the expectation value of position, but don't worry. So we know that there is something called the wave function. This wave function represents the state of our quantum system, and the Schrödinger equation tells us how the wave function evolves in time and how it varies in space, or at least its value in space. So the evolution of the wave function is stated in this equation. Not all solutions to these equations are real wave functions. The only physical meaningful wave functions are the ones that are normalizable. So the integral of their modulus squared is 1. Moreover, if we want to find the average value, it's called in quantum mechanics the expectation value, but remember, it's the average value of some quantity measured at the same time on several systems in the same state. You collect all this data and you want to find the average of it. You do it by taking the integral of psi star times this operator acting on psi. And what I mean by it is that everything in classical mechanics, every quantity of interest depends on position and depends on momentum. If we know the position and velocity, we can describe everything of our system. In quantum mechanics, this notion is modified in some way. We basically need to replace x by the x operator, which is the usual x coordinate, so nothing crazy, and the canonical substitution for p. So the momentum for that quantity to become its operator, well, you just need to replace p from the classical mechanical version with this quantity here. And thanks to that, we can find the average value. Moreover, we can also find the average value of its square, and thanks to that, we can find the spread, so the variance of the distribution. So we might have a narrow distribution or a larger distribution. And this is what we've seen so far. But let's start by kind of simplifying the Schrödinger equation. So we said, okay, let's assume that the potential is constant. This is something that happens in nature. So why should we care about time-dependent potentials when we have a lot of time-independent potentials? Of course, sometimes you can simplify this equation, but for now we want to study time-independent potentials, potentials that simply sit still. And we're going to do it now. So, time-independent potentials. Is there anything that we can do? So let's remove this t from the Schrödinger equation. Is there something we could do to solve this differential equation? Well, we have, obviously, psi depends on time and depends on space, the location in space. So we can assume that, to solve this equation, that our psi, that is both x and t dependent, can be simplified to, a part which simply depends on x times a part that simply depends on time. This is called the separation of variable, and it's always used in mathematics. So here's another restriction. So you see, it is not just this restriction, we also have this restriction, but then we're going to recover all the missing solutions later on, so don't worry about it. Now, why does this clever trick work? Well, let's replace this expression into here. So we do have a I times h bar, and then we have the partial derivative of this quantity. This is a product, but the first part is time independent, so it's a constant under this differentiation with respect to time. So we can just put it outside our partial derivative, and then we have partial this part partial t. But this quantity simply depends on t, no other dependence, so we might as well write it as a normal derivative, because this phi function depends only on time. Okay, we're making progress. Then let's look at the second part of our equation. Here instead we have an x dependent, an x partial derivative. So what can we do? Same thing. Phi of t is spatial independent, so we can just write it outside this partial derivative. So let's rewrite this nasty constant. We have phi of t, and then we have our derivative, second derivative this time. It's not a problem. We're differentiating only this part. Only depends on x, so we can do the same trick. And then we have our time-independent potential, and I'm specifying that it is time-independent, times psi, and psi has become the product of these two pieces. Now another clever trick is going. We want to put everything dependent on x to one side of the equation and everything dependent on t to the other side of the equation. And you'll see why we're doing it. So one way to do it is to simply divide, so multiply by 1 over the wave function, so psi of x, phi, I always forget how to pronounce these letters, phi of t. Now, we're dividing by the wave function. Are we still adding a new restriction to our wave function? Well, psi equals 0 is the solution to this equation, and we cannot divide by 0. Is it a problem? No, it isn't, because the wave function psi equals 0 is not normalizable, so it does not represent a physically a physical system, a system we can find in our universe, because it cannot be normalized. How can you find a factor that multiplied by 0 gives you 1? It doesn't exist. So this wave function, it's not normalizable. So psi equals 0, we don't care about it. So we're not restricting our psi. Because remember, we need to consider these two and not just the Schrödinger equation. Okay, so let's do this. H bar. So we're dividing by this, so the 2 cancels, and we remain with 1 over phi of t, d phi by dt, equals to minus h bar squared over 2m. Same thing happens here, but this time with the other function. We have the second derivative, and the potential remains without the wave function multiplying it. Now, here's the cleverest trick ever. I really like it. So, this part is time dependent. It only depends on time. This part only depends on x. And remember, x and t are independent variable. There is no dependence between x and t. X cannot be represented as a function of t, and t cannot be represented as a function of x. They're independent, they vary independently. But if they do vary independently, then this means that there is no way these two sides can be equal to each other, because this side is varying on its own and this side is varying on its own. So the only way these two sides can be equal is if both of them are equal to a constant, because if they're both constant, then they can be equal. Otherwise, this depends on x, this depends on t, and there's no way they could be equal to each other. But thanks to the fact that they're constant, otherwise this cannot be true, we can separate the variables. Remember, this is a condition we simply comes from the fact that t is independent of x. So we do have these two equations. Let me write them down here. We first write our time-independent equation. So we have IH bar d phi by dt 1 over phi, remember phi depends on t, but I'm tired of writing phi of t, equals to this constant, I'm calling it c, okay, now let's turn to the second equation, and minus h bar squared over 2m, let me check whether I'm recording, okay, perfect. I'm also running out of memory, so I hope we can make this in time. So we have this constant, then let me write down the second derivative. Then we have this factor, and then we do have our potential. And this also equals to the constant. When writing in Spider-Man style with red and blue markers. Perfect. Now, we don't like this factor in the denominator, so we might as well bring it to the other side of the equation. And I'm doing it here without rewriting everything all over again. So let me do it right here. It's just a simple multiplication, nothing crazy, nothing new. Okay. Now, to solve the initial Schrödinger equation, we just need to solve these two equations and then multiply them together. Let's solve the time equation. I'm referring to this as the time equation, and this equation is called the time-independent Schrödinger equation for obvious reasons. So let's stick to the first one. This is a simple differential equation. I mean, we have d phi by dt equals to, let's bring this factor to the other side. Remember, dividing by I is the same as multiplying by minus I. So minus this is a c over h bar, and we have phi again. Now, we need to solve this differential equation. It's simple. The solution is the general solution to this is this one, where a is just some constant times e to the minus ic over h bar t, and this is our solution. Now, we might as well drop this a, because we can incorporate this constant factor to the other equation, because at the end what we care about is this capital letter psi, and so we can just bring this constant to this other equation. I'm sorry I wrote psi here because it comes to me naturally. Here I used a different Greek letter, so, well, this can arise confusion. Most of the time in textbooks you find psi in capital letters has the usual time-dependent wave function, and psi in as the time independent solution. but I cannot, write this in a different way than psi in capital letters. So I chose to use this letter instead to record this video. But I know it can arise confusion, so we'll see how to cope with this. By the way, remember that, let me do this. Let me replace this psi. I think it's better for you and me. So let me replace it. Perfect. And we do have these two equations. Now, can we solve this equation here? Well, we first need the potential. We need the potential to solve this equation. Without the potential, we cannot simplify it further. We cannot solve it directly. We need some information about the system. So that's the time-independent Schrödinger equation. And this is what we're going to be interested in the next videos, because that's the equation we're going to solve. But for now, we have a simpler class of solutions. Now let me erase the whiteboard and we're going to continue. Okay guys, now it's time for the cool part of this video. What do we care about this type of solutions and how to recover the general solution to our problem? Well, firstly, let's look at the normalization of this wave function. Here, instead of having the well, we need to put in this equation our psi, capital letter psi, and let's find out what happens. So we have psi of x. Sorry, this I don't remember the name of this letter. Please write it down in the comment section. The time-independent solution, time times this factor, but it's conjugate, so we do have e to the ic over h bar t, because it's basically it's conjugate, times the time-independent solution times e to the minus ic over h bar t. Now we found in the last video that the probability is constant, but if it's constant, it doesn't mean that the shape of the probability distribution changes with time. But for these particular solutions, these are if you multiply these two, you get 1. So we find that we can replace our probability density, which is the inner part of this integral, with these two solutions. So the shape of the probability density doesn't change with time for these separable solutions, and the same goes for the operators. In particular, if we want to find the expectation value of x, we take the product of these two, we multiply by x, because the x operator is simply equal to x, and we find that the expectation value of x is indeed constant for this very reason. But if the expectation value of x is constant, we know that n first theorem tells us that and since x is constant, the n first theorem tells us that the velocity, the momentum, the expectation value of momentum, which resembles the classical equation but with the average instead of the classical variable, the derivative of a constant is zero, so the expectation of momentum doesn't change, the expectation value of position is constant, the probability distribution doesn't change, so they're nothing really happens in those states. But the best property of them is the energy. And That's cool, because the energy is the most important property of them. Because we still don't know what the constant C is, but it will turn out to be something incredible. So, how do we find the expectation value of the energy? The expectation value of the energy, well, what is the energy operator? Well, the energy operator is the Hamiltonian. So the Hamiltonian in classical mechanics depends obviously on x and p, and this equals to p squared over 2m plus v, the total energy of the system. We call it the Hamiltonian. Now we need to do the canonical substitution, and this becomes minus h bar squared over 2m d by dx squared, plus the potential remains the potential because of this substitution. And this is our Hamiltonian operator. But if we take, so that we don't care about the wiggle factor here, so if we take psi, the only time-independent part, its conjugate, and we apply this operator on this psi, we get basically, it resembles the Schrödinger equation. In fact, all this part here, which is what we're looking for to find the expectation value of the energy, simply equals to C. When we apply this operator, this is called the Hamiltonian operator, we get C times the time-independent solution. Because we're applying the operator on psi, those wiggle factors cancel out, and we remain with this equation. But we can bring the constant out, and this simply equals to the modulo squared of the time-independent solution. And we found earlier that this equals 1, so at the end of the day we get C. Okay, the expectation value of the energy is C. Nice. But there's also another interesting property. What is the distribution of the energy? Does it look something like this, or is it narrower? Well, we're going to find out. How to do it? Well, we need to find the spread of the distribution, and the spread of the distribution referred to the energy equals to, mathematically, the square root of the expectation value of E squared minus the expectation value of the square bracket, the angular bracket, of E squared. This is what we need to do to calculate the spread of this distribution of energy. So let's do it. We have to do the same thing to find the expectation value of the energy squared, because we already have the expectation value of the energy, and we found that it is equal to C. Well, what we have to do is to take our interval. We have this time-independent solution conjugated times 2 times the Hamiltonian operator. But 2 times the Hamiltonian operator, it's the Hamiltonian operator applied to the Hamiltonian operator of the time-independent solution. But we found earlier that this equals C times C times the time-independent solution. But C is a constant, so we can bring it out. But H on the time-independent solution is again C times the time-independent solution, and this times this is the probability density, so at the end of the day we get C squared. And if we put this and this into our variance, we find that the variance equals 0. There is no spread. The energy has a particular value. It is not spread in space. So what's the most important thing of separable solutions is that they are solutions with definite energy. And the most general solution to this equation is the sum of all the solutions with a particular energy. It could be a discrete sum, a finite discrete sum, infinite discrete sum, or even a continuous sum using an integral, but we'll see that in another video. Hope you enjoyed it, subscribe to my channel, and see you in another QM video.